Hello and welcome to the Ocean Sites virtual conference. I'm Nathan Anderson, a member of the Ocean Climate Stations group, and today I'll be presenting on measurements in the deep ocean, existing scientific questions, and visions for the future of deep sea observation. Today's presentation will be split into 4 parts: a brief introduction to ocean climate stations, followed by individual sections about abyssal measurements at our 2 moorings, Papa and Kio, and ending with a vision to 2030. In the 2 mooring sections, I'll present some raw data to highlight the measurement issues experienced and the subsequent data handling issues that arise. I'll also go over the underlying causes of drift, data spikes, and other abnormalities in the data. In our vision to 2030, we'll propose site expansion ideas and explore how future observation systems might be designed to detect benthic storms, which are active in the Kio region, stirring up sediment and producing strong currents in an environment otherwise assumed to be quiescent and calm. In fact, currents over 30 centimeters per second have been detected near the seafloor in previous studies of the Kuroshio extension. Lastly, I have to put in a plug and direct you to our data download and visualization webpage at the listed URL. The site allows selection by mooring, time, variable, and resolution, and produces netcdf or ASCII output files and plot plus data visualization for quick publication quality plots on demand. To get us spatially oriented, here's a map of the 2 moorings, Kio and Papa, currently maintained by the Ocean Climate Stations group. Kio is located off the coast of Japan in a dynamically active region within a recirculation gyre south of the Kuroshio extension jet. Papa, on the other hand, is located in the northeast Pacific and represents a continuation of ship-based records going back to around 1950. Both moorings are part of the wider community's objective to increase the number of stations with these long-term climatological records reporting on an array of essential ocean variables as well as meteorological data. The OCS group continues to evolve and continually strives towards seamless data access. To that end, ERDAP and LAS have emerged as powerful tools for their ability to transform data between formats and also their ability to quickly plot up data, but the interface can be overwhelming to new users and those wanting a one-click data shop. Therefore, we have designed web pages around ERDAP that are more targeted to a particular dataset and can really hone in quickly on your desired data. It's certainly possible that other datasets could take a similar approach. Let's switch gears a bit to talk about abyssal observations at each mooring site. Let's start off with the Papa site, looking at raw data. Pictured here are pre-cal and post-cal data from each deployment in blue and red, respectively. At first glance, we can see several data issues jump out. First off is bottom strikes. Bottom strikes occurred in the early days due to the mooring line slacking when the buoy passed over the anchor. The impacts were detectable in the pressure time series, and with enough impacts it degraded data quality in other fields as well, which ultimately had to be flagged. Whether due to bottom strikes or from other causes such as debris or interference, we do see minor outliers throughout the record that require quality control. The jumpy conductivity witnessed in years 1, 2, and 7 are associated with bottom strikes, an issue that's since been remediated by tightening the scope of the mooring line. But as you can see, the issues with the Papa dataset are relatively minor. Let's move on to the Kio mooring located off the coast of Japan. Referring back to our map, the Kio mooring is located here. In this figure, you can see the Kio mooring within the recirculation gyre of the Kuroshio extension jet. The jet is shown here by the tightly packed isopleths, which represent approximate streamlines of geostrophic flow. Within this regime, the Kio mooring has historically held one deep instrument 56 meters off the seafloor. After noticing recurring salinity drift in the deep instrument, we added a redundant instrument at 56 meters and a third sensor at 90 meters to gauge whether the drift changed with depth and to confirm that the drift was not instrument specific. So what did this drift look like, and what questions did we seek to answer? As you can see from the time series, salinity drifts fresh by 0.03 to 0.06 PSU per deployment before being restored to around 34.69 PSU with each new deployment. This plot mimics the Papa plot with the exception that color now represents separate instruments at 56 and 90 meters off the seafloor, rather than a single instrument's pre-cal versus post-cal, because interpolating from pre to post-calibration didn't serve to correct the drift at Keough. Also, you may note that we had one lost year where the instrument failed to write to its data recorder despite review of diagnostic files that suggested proper setup. While pressures shifted slightly on year 3, the time series of potential temperature was continuous, indicating a good handoff between deployments. Salinity is calculated from temperature, pressure, and conductivity, and the salinity drift observed here would require about 100 decibars of pressure drift, not offset, to account for the salinity change. In other words, a pressure sensor that is offset by 100 decibars would only serve to shift the salinity time series up and down, not really affecting its slope. So based on the trends, it should be apparent that a conductivity problem is responsible for the bulk of the salinity drift here. Finally, note that an additional instrument was deployed slightly higher in the water column in the 2018 to 2019 deployment. It was surprising to find that salinity drifted more at 90 meters than at 56 meters off the seafloor, considering the nepheloid layer, a possible cause for the salinity drift, typically becomes less concentrated with height. The most important scientific questions buried in the Keough dataset were: what causes our salinity drift? And why might deep temperatures increase over a 4-year period, but presumably not over longer periods of time as evidenced by decades of previous CTD cast data? We dug into both questions in Anderson et al. 2020 and will summarize the highlights here. 2 intriguing temperature observations were noted to explain deep ocean temperature variation. First, periodicity was noted in the temperature power spectra, offering the interesting possibility of a teleconnection to the surface or the presence of internal waves. Second, a common metric categorizing the state of the Kuroshio extension called the Kuroshio extension index was plotted alongside a smoothed weekly average temperature time series. These time series showed a moderate inverse correlation, suggesting that higher temperatures coincide with lower dynamic stability, a weaker jet and gyre, a more southerly jet position, and higher jet meandering. Switching to salinity, we saw that salinity drifted over the course of each deployment. Since postcals weren't indicative of drift, we set about determining if and when the instruments self-correct. We isolated the data during ascent, given here as plus symbols, and compared it with historic CTD casts, the colored lines. Interestingly, accuracy was immediately restored when each SBE instrument began its ascent. We formulated 2 primary hypotheses to explain salinity drift. Both involve accretion of material within the conductivity cell that constricts the cell with time. In fact, we learned that a film just a few microns thick could skew our salinity by 0.03 psu. Since we haven't seen this drift at other sites, our hypotheses had to identify what might make the Keough extension region so unique. Perhaps the most likely explanation is benthic storms. Benthic storms are long-lasting storms associated with baroclinic instability in western boundary current jets, capable of lofting sediment into the water column. Additional evidence for this comes from a nearby Jamstec sediment trap, which measured high concentrations of bottom-sourced material called aluminosilicates at 700 meters off the seafloor. The figures here show a potential link between the upper ocean jet and bottom pressures, as well as heightened eddy kinetic energy at depth in proximity to Keough. To summarize our findings, slow accretion of suspended sediment is the primary culprit for salinity drift. The cumulative drift, however, clears during ascent, suggesting that a pumped instrument that clears the conductivity cell at regular intervals may see superior performance in the deep ocean. Temperature, on the other hand, is potentially linked to surface influence, whether atmospheric or related to the state of the western boundary current jet. We've learned a lot from deep observations at Keough, with our most concise conclusions listed here. OCS intends to continue monitoring abyssal temperature and salinity to pick up on long-term changes and improve best practices for deep-sea measurements. As we look to the future, we hope to more fully characterize the nepheloid layer associated with benthic storm passage, a unique feature in the Keio region. Exploring the size, shape, and distribution of suspended particles in the deep ocean may contribute to our understanding of the variable rate of salinity drift and potentially reveal ways to correct or improve our measurements. Finally, I want to conclude this presentation with a vision to the future. One of the objectives in the future of OCS observations is better understanding the scale and scope of benthic storms. With this in mind, we foresee actionable modifications to our deep ocean observing suite. Things like being able to detect storm events based on current meter data, nephelometers, or other instrumentation able to quantify the distribution of particles suspended in the abyssal ocean. Though we aren't certain how the future of observing will be impacted by worldwide events this year, a long-term goal might be to enable real-time observations from the deep ocean. Limited transmissions from the ocean floor might be possible leveraging DART-like technology, whether the instruments are attached to the mooring anchor, which is already quite crowded, or by way of a separate lander. Thank you for listening to this presentation, and please ask questions during the virtual session. Thanks.